It's a great pleasure to talk to all of you from a little town called Gawler in Australia. Lightning. Everybody in this symposium would know that one of the great unsolved problems of the world has been to explain ball lightning, but there's no general agreement. I want to talk about another two unsolved problems related to ordinary lightning. These two problems are firstly, why are leaders of lightning stepped? And secondly, what is going on in the long column of lightning between the step and the cloud? These issues are important in that one needs to know what's really going on in lightning to check the validity of methods of lightning protection, like the rolling sphere method. The proposal I'm putting forward is not complete in that one step of it is impossible for me to do, firstly because of unknown charge structures within clouds, and secondly because of unknown cross sections for excitation of oxygen metastables by nitrogen metastables. Now back to ordinary lightning. I'll just check whether I have a pointer here that works. Yes. You will have all seen many photographs of lightning, such as are shown here. And these photographs are taken by putting a camera on a tripod at night and aiming at a cloud where you hope there'll be lightning. And then if you're lucky, there is lightning, and you then close the shutter and develop the film. And when you do that, you get a picture of an integrated picture of the whole of the light during the whole of the lightning strike from beginning to end. And what is seen is the very thick channel of the return stroke and the faint channels on the side. And
you want to go forward a slide? Next slide?
Yeah. This slide illustrates a cloud which is charged up to a high voltage, and one gets these streamers or leaders coming from the cloud branching out. And when one of them hits something tall on the ground, be it a flagpole or a cathedral spire, you get a return stroke. Now, the next slide shows the big mystery that arose from high-speed photographs. And this is a famous photograph reproduced in the textbook Lightning by Rakoff and Newman. And it's a photograph taken by Berger and one of his associates at the San Salvador mountain in Switzerland in 1966. And it's a street photograph where instead of having a stationary film, the film here is moving very rapidly to the left. And it's very rapid in that it's gone this distance in 1 millisecond. Now, if lightning would just be a continuous development of a leader from the cloud going to the ground, one would have a line here going to the end, and then as time goes on, this line would extend going down. But there are two big unexpected things here. First of all, only the tip lights up. And secondly, between these successive tips, it's dark. And this is the stepped leader. Now, to illustrate that in detail, which we need to do to form some sort of theory, here's just a description of what follows from that photograph, which has been reproduced many times more accurately by other people. You have a cloud which charges up, and the first thing that you see is a long step, generally can be 50 meters long, and it forms in a microsecond. And it lights up and goes a whole microsecond for 50 meters, and then it goes out. And when it goes out, you don't see anything or very, very faint light. And I've drawn it here with different color, indicating that it's dark. And it's dark for the order of 50 microseconds, which is a long time compared with the formation time. Then a next step starts, also 50 meters long, also in a microsecond, and it starts at the end of the first step, but the first step doesn't relight. Then after that, after a microsecond, this step goes out and is dark, like the first one. And then after another 50 microseconds, you can get a third step, and it can branch, and you get branching of branches and the like. Well, one question is, why are things stepped? And secondly, this column is a mystery in that it's dark, no light, but there are evidently electrons there because it's highly conducting, and the field seems to be near zero because these columns can be kilometers long. They can be 10 kilometers long. Now, the next slide is the answer to my proposal given early, and now an explanation of each step. The first step is a cloud, and you can call that as a high voltage source. And in the calculations I do, this source is 2 megavolts. But textbooks give cloud voltages of 200 megabytes, some of them bigger than that. Then this step forms, and the step goes forward using up potential, and then at the end of this step, the potential approaches near Earth and the step stops. There are two big processes going on. Electrons get energy energized by the electric field and can ionize oxygen, creating another electron, and you get an avalanche growing, doubling, doubling, doubling. That's in regions of high field. In regions of low field, electrons attach onto oxygen. The attachment rate is very high, and they form negative ions in nanoseconds, and negative ions don't do anything very much. But now, once this step is formed, even when it goes out, there's still a voltage left, may not be quite 2 megavolts, but there's a voltage there, and there are electrons there, and we know that electrons hitting oxygen can create excited oxygen, and there is the first excited state of the oxygen molecule is the singlet delta state, which is metastable. Now, the essence of my proposal is that in the 50 microseconds that this thing is dark, slowly one develops more and more metastables because they don't go out. And if the density becomes very large, and by very large I mean 10 to the 17 per cc, and 10 to the 19 per cc is atmospheric pressure, so it's like 1%. If you achieve such high densities, then there is another reaction. The metastables hitting oxygen negative ions can detach the electron, so you have an electron released and the negative ion is destroyed and you get another oxygen molecule. Now, the proposal, the consequences of this is that this column, and the column can be very long, is that because it's conducting, the potential at the tip of the column before the step approximates that of the cloud. And in this column, you have many, many metastables which are detaching electrons for the negative ions, but those new electrons are attaching onto oxygen to form negative ions. And you have an equilibrium between detachment and attachment, and no current, but a very high electron density. Now, I need to talk a bit about singlet delta oxygen molecules, which are known, and there are huge review articles written on their properties. The symbol given by people in the molecular game is A1 delta G. The energy required to form such a metastable is 1 electron volt. And in most things, if electrons hit an atom or a molecule and excite it, generally that excited state falls back in the order of a microsecond, giving out light. But for singlet delta oxygen metastables, the radiative lifetime is about an hour. However, it can be destroyed through collisions. I'm talking, and this is crucial to the whole theory, of very high metastable densities of the order of 1%. And such densities have been measured in discharges at 1 atmosphere. And there's a reference here given. And the reference is for medical applications utilizing singlet delta oxygen, which will dissolve in water, just as oxygen does, and will dissolve in blood. And there are various proposals as to therapeutic effects of the oxygen molecules. And the crucial element, I repeat again, is that oxygen metastables hitting negative ions can detach the electron, making the region conducting. And if you have millions of these, you can convert a step from being insulating to being conducting. Also, I mentioned that there are nitrogen metastable states, and the nitrogen metastable states have an excitation potential of only 0.29 eV, and there are many of them going up to 60, and you have a whole chain of them, and they rattle around hitting one another, causing various excitations and de-excitations, and they can enhance ionization. And there is some evidence that nitrogen metastable states can increase the excitation of oxygen metastables. But it's known definitely and remarkably that oxygen metastables are not quenched by nitrogen. The quenching rate in nitrogen is 0. Now, these metastables in oxygen, there are excitation rates which are known. The two basic common, usually dominating mechanisms are ionization to form new electrons, and at high voltages you get very high ionization, and at low voltages you get no ionization. And then there's attachment of electrons to form negative ions, which attachment rates are very high at low fields because the electrons don't have much energy and they just attach. And the metastable rates for a whole range of electric fields below the ionization field are about an order of magnitude higher than attachment. So metastables get created more rapidly than other particles. Now, equations, of course, exist for the rate of change of electron densities, positive ion densities, negative ion densities, and metastable densities, all subject to changes in the electric field due to Poisson's equation. And these equations can be coupled and solved. And I've done it for 2 dimensions for one particular model case. Normal equations for normal discharges just do electrons, positive ions, and negative ions and leave out the metastables, because the metastables at the start do nothing. They're metastable and they don't do anything, so there's not much point in calculating them. But the reason for calculating them is that if there's a chance for them to accumulate, and I'm suggesting they do accumulate due to the 50 microsecond dead time of the step, and then if they get really large, the detachment can produce new electrons. Going through one of these equations, rate of change of electron density depends on ionization and attachment. And of course, if the electrons move, the densities change. Electrons can combine with positive ions, and electrons can be formed by detachment. Kd is a detachment coefficient, which is known for metastables and oxygen, and the production of new electrons is given by the rate coefficient times the negative ion density times the positive ion density. And there are similar relations for all the other particles. Now I want to do a calculation, and I want to start off with initial ionization in the cloud. And I don't know what charge structures there are in a cloud, but I want to get a field of more than 25 kV per centimetre to get ionization. And I've chosen a cylindrical column of negative ions of length 5 meters and diameter about a meter. And at the tip, I've put a density of negative ions of 10 to the 9 per cc, and here it's only 10 to the 7. And this whole structure is chosen so I get a field urging electrons to go downwards, where I'm going to try and simulate a leader. Now, with that initial structure, which is arbitrary, and if you change that, you get all sorts of different answers, the calculated electric field at the tip here is of the order of 40 kV per centimetre. And for ionization, you only need 25 kV per centimetre. So this high electric field is going to start producing electrons and ions, and the field everywhere else is lower. And the potential of all this, the calculated potential, is that this tip here has a potential of 2 megavolts. And for a cloud potential, 2 megavolts is low. As I've mentioned, books give cloud potentials very high, up to 200 megavolts, 500 megavolts. I think those high values are suspect, but doesn't matter. Now, with all this, we start calculating all these particle densities and see what we get. And here are the solutions. The electron density at 1 microsecond here is a blob, and there's different scales on radius and Z, and it's a roughly hemispherical blob of density 10 to the 9 per cc. the metastable density is much more than 10 to the 9, and here it goes up to 10 to the 12, 10 to the 13 per cc because the cross-section for metastable is so high. But even though that cross-section is high, the actual metastable density doesn't do very much. And negative ion densities here are the order of 10 to the 11, 10 to the 12, which is higher than the electron density because that pulse is starting to stall. And here are densities of positive ions, which are much the same as the sum of electron density and ion density. And now here, the electric field at the edge of this plasma started off being 40 kV per centimetre, and here the electric field is getting less than 25 kV per centimetre because of the stalled first step. And potentials here are of the order of 1.5 megavolts. Now, the point of this proposal is that metastables do things, and you have to get a lot of metastables, which means big computer times. And to get the qualitative effect of metastables, I've just increased the metastable density by a large factor and just seen how everything changes. And the changes initially from densities of metastables of 10 to the 11, 12, 13 is nothing. But if the metastable density gets to the order of 10 to the 17, all of a sudden there's a dramatic change with the electron density changing from 10 to the 9 to a calculated density here of the order of 10 to the 13, 10 to the 14. And metastable densities here, I've just multiplied by a large factor, and the densities of metastables here are artificially made orders of magnitude larger, which I'm proposing happens during the 50 microsecond step. Then the effect of negative ions is to be reduced to well nigh zero, because all these metastables are detaching electrons from the negative ions, converting the negative ions to be electrons. So here, the negative ion density started off at something like 10 to the 12, and here it's gone down, the bottom is something like 10 to the 9, and the electron density is very much lower. Then positive ion densities are changed a bit, but not much, because electrons and metastables and positive ions don't do much to positive ions. Then finally and dramatically, this blob of plasma, which has now got many metastables in it, the metastables have converted the negative ions largely to electrons. So the electron density here is very large. I've forgotten what it was. Electron densities are of the order of 10 to the 13. And in most gas discharges, the electron densities are of the order of 10 to the 11. So this is really conducting. Well, because this is really conducting, the potential, it's like attaching a wire, a conducting wire, to a high voltage source. So this connection with the cloud raises the potential to that approximating the cloud. But at the edge of this conductor, the field is increased, and it's increased enormously from 25 kV per centimetre to over 100 kV per centimetre. So now, with the glowing step converted to being a conducting step, you have a very high field at the edge, the bottom edge of that conducting step, and that high field can produce a new step. And there's furthermore a higher field at the back, so you have some influence of producing increased ionization up towards the cloud, which was visible on the first slide I showed from Berger with the moving film. Finally, and this is my last slide, I'll go over all this again, but this slide is primarily to describe, I've finished describing the steps, and now this is describing what goes on in the column. And in the column, I'm saying there are two reactions going on. Electrons are attaching to form O2 minus, but O2 minus is being destroyed by metastables to produce new electrons. So here's an attachment rate of a production rate of negative ions, and here's a destruction rate of negative ions. And these rates are very high and become equal in nanoseconds. And as a consequence, you get a steady state. And we just equate the attachment rate, electron density times attachment coefficient, equal to detachment rate of negative ions with metastable rates. And you equate those two rates. And now if you divide through by N minus, Ne over N minus, the electron density compared with the ion density depends on a bunch of numbers here, which are just material constants, which are all known, times the metastable density. And you can see here, if the metastable density is very large, the electron density becomes very large compared with the negative ions. But it has to be of the order of 10 to the 17, like 1% metastables, for this to be appreciable. And you now have this strange situation of all these steps joined together, forming a column. And as I mentioned, this column can be kilometers long, and the mystery is it's conducting, and what is it? Well, I'm saying it's electrons formed from detached electrons from the metastables. But everybody knows that if you have a large electron density in any material, be it a metal, the electric field within that is zero, simply because if you have an electric field in a plasma region with many electrons, the electrons move to the edge of the plasma to make the field zero or near zero. Now, because the field is near zero, there's no light emission, even though it's conducting. Furthermore, there's no current. Many people say, oh, these electrons come from the current, a current from the cloud downwards. No, the electrons are produced locally. So there's a very novel situation I'm proposing for the column. And then there's a high field at the sheath, at the edge of these conducting steps here, which produce the next step. That's my talk.